So to find the area bounded, you always want to make the graph first. So this is a cardioid, its sine, so it's symmetric with respect to the y-axis. So I know just by plotting a few points, it looks like here and here and here. Okay, so there's the cardioid. So I want to find the area bounded by the first and the fourth quadrants. So that's here and here. So that means I want to go a negative pi over 2 to a pi over 2. So area bounded is the integral from negative pi over 2 to pi over 2. And to draw the sectors, let me just get this in a different color. Remember, sectors always start from the origin and go out to the curve, right? And it's the angles on the sectors that are getting thinner, smaller and smaller, so they end up just being little tiny sectors like that. All right, so it's 1/2 2 plus 2 sine theta squared d theta, and we're just setting up this integral only. Okay, so r equals sine of 4 theta. So sine of 4 theta, I know this is a flower that has 8 petals. And I'm sorry, that since this n is even, this is going to be 2 times this number of petals, right? So that gives me 8 petals. That's back up to explain myself there. So what is the range of 1 petal? That's because I'm always going to be trying to find the area bounded by 1 petal. And from what you know before, from our notes, it's pi over 4, pi over n. So to find the area bounded by 1 petal, the area is going to be 0 to pi over 4, 1/2 sine of 4 theta squared d theta. That's the area bounded by 1 petal. All right, so this is the cosine. So the cosine had a different boundary limits. So this was going to be negative pi over 10, 2 times this number 5, to pi over 10. So the area of 1 petal would be negative pi over 10 to pi over 10, 1/2 cosine of 5 theta squared d theta. So knowing those boundary limits is going to be really important. All right, so these are just extra problems. So area inside 1 petal of sine of 6 theta. So what could be a good idea for you to do is to turn off the video and just kind of work on these on your own. Oh, I haven't done any of these inside outside yet. Oh, that's good. Let's do these. Okay, so this one here, the sine. So I know that it's going to be a flower with 12 petals. So my area bounded, the angles that bounds 1 petal is going to be pi over 6, 0 to pi over 6. And so this says find the area. It does not say set up only, so let's go through and finish solving this. So I have 1/2, 0 to pi over 6, 2 sine of 6 theta squared d theta. All right. So let's do this. So 1/2, this is going to give me a 4. Oops, not a very good integral sign there. 0 to pi over 6, 4 sine squared of 6 theta. So this will come outside here to give me a 2. And you know to take the antiderivative of sine squared, I'm going to need the half angle formula. So that's 1 minus, sine squared is the minus, and it's doubling this angle, so 12 theta inside here, 0 to pi over 6. So this 2 and this 1/2 cancel. And so to take the antiderivative of 1, I get theta. Take the antiderivative of here, I get 1/12 sine of 12 theta. And then I'm plugging in 0 and pi over 6. So I get pi over 6. If I plug in pi over 6 here, I get 2 pi, so that's 0. And then plugging in 0, I get 0 minus 0. All right, there it is, pi over 6. That's the area bounded by 1 petal. All right, so now let's do these in different colors. So let's do this, which is the circle that just takes 0 to pi to go around. and it looks like here, and it's going to go out to 2. And let's do this, r equal 1 in blue, and it's going to be a circle centered at the origin, 1 like that. Okay, so we want to find the area inside the red. Whoops, let me try that again. Inside the red and outside the blue. Inside the red and outside the blue. This area here. So I'm going to encourage you not to color it all in, because I want to be able to still see the sectors. So let's look at these sectors. So this sector here comes out to here, right? So this is, the sectors always have to start at the origin. So this black sector coming all the way out here gives me more than the area I want. So what I want to do is I want to subtract off this sector, right? I want to take this away. So just like in back when I had rectangles, right? So if I had this up here, so if I had a rectangle that went all the way up to here, then I had this curve and I took away this, right? I went all the way up to the black and took away the green, and then I was left with the area that I wanted, right? Just that part. So I'm going to do the same thing here. So I'm going to have 1/2. So then the outside area, subtract off the function that gives me the inside area, right? D theta. Okay, so going all the way to the outside would be the red function, so that's this 2 cosine theta, and I'm going to subtract off the green. So the curve that gets me to the green area here is the r equal 1 squared. And so from where to where? So, let's see. It's going to be all of this red dotted area, but let's use our symmetry. We know that this area from here to here is going to be doubled, correct? So let's do 2 times all of this, and I know I'm going to start at angle 0, right? And I'm going to go to where they intersect. So where do these 2 graphs intersect? So this intersects at... cosine of theta is 1/2, and where do I know cosine of theta is 1/2 in the first quadrant? That's going to be pi over 3. So the angle here would be pi over 3. So canceling the 2's and the 1/2s, I have 0 to pi over 3 of 4 cosine squared theta, cosine squared theta minus 1 d theta.